Okay. Hello, my name is Jacob Payne, and today I'm going to be solving problem 513 for the bonus work assignment. So, problem 513 says this. Suppose you have two infinite straight line charges, lambda, a distance d apart, moving along at a constant speed v. How great would v have to be in order for the magnetic attraction to balance the electrical repulsion? Work out the actual number. Is that a reasonable sort of speed for these electrons? Okay, so we can start with this kind of setup that I have in the top left corner, along with some very important equations. 513, which states that the current is equal to the line charge times the velocity of the charges. And equation 540, which shows that the magnetic force per unit length is equal to mu naught over 2 pi I1 I2 over d. And this is for the magnetic force per unit length of two line charges that are a distance d away, carrying currents I1 and I2. Now, for this case, the currents are in the same direction, and they are actually going to be the same magnitude, seeing as though we have I1 being lambda v, and I2 is also lambda v. Plugging that into equation 540, we find that the magnitude of the force per unit length of the magnetic force between the two is lambda v squared over d. Now we will be using equation 2.9 to find the electric field at a distance r away from a wire carrying a line charge. And that will be equation 2.9. So filling that out, if we're assuming we're using the electric field from line 2 on line 1, that is distance d away, we have that the electric field is equal to 1 over 4 pi epsilon naught 2 lambda over d, and that is in the positive z direction. By the way, we're calling up z, to the right y, and out of the page x. So the force from that electric field we know to be Q times the electric field. That being said, the force per unit length is then the force divided by length. Now we know that the charge divided by length is represented by lambda, which is the line charge. Now, the question is, how fast does the velocity need to go in order for the magnetic attraction to balance out the electrical repulsion? The force from the electrical repulsion is in the positive z-axis. The magnetic attraction is in the negative z-axis, and this is if we're talking about line charge 1. We know that the magnitudes would have to be equal. Therefore, we have mu naught over 2 pi lambda v squared over d is equal to 1 over 4 pi epsilon naught 2 lambda squared over d. Now we can do some cancellations here. And we end up with u naught v squared is equal to 1 over epsilon naught. That being v is equal to 1 over the square root mu naught epsilon naught. If we plug that into a calculator, we find that v would have to be 2.999 times 10 to the 8th meters per second. We know that the speed of light is about 3 times 10 to the 8th meters per second, and so this is a very unrealistic speed that v would have to reach in order to balance out the magnetic attraction and electrical repulsion. Therefore, the electrical repulsion will dominate in this sort of scenario. That will be all. If you have any questions, you're more than welcome to ask and let me know.